Imagine that the very beginning of our universe, an event we commonly call the Big Bang, wasn't a solitary explosion from an infinitesimal point, but something entirely different. A white hole expelling matter and energy from an already existing distinct universe. This intriguing concept invites us to journey through interconnected dimensions, exploring cosmic phenomena that defy our current understanding of physics. It even suggests that our entire reality might be nothing more than the residual output of a neighboring cosmos. We stand at the precipice of science's ultimate enigma. Conventional Big Bang theory postulates that all matter and energy originated from a singularity, an infinitely dense point where our physical laws completely break down. The enduring question for cosmologists, spanning many years, is how existence could possibly emerge from absolute non-existence. The mathematical models hold true right up to that initial moment, then devolve into incoherence. Infinite temperature, infinite density, even the concept of time loses all meaning. It's akin to encountering a divide by zero error on a calculator. The display simply shows an error. This is precisely what happens when we try to comprehend the universe's absolute first instant. Every equation we use to describe reality falters under the conditions of the Big Bang. While we can trace the universe back to incredibly early stages, that final step to true zero remains unattainable. Numerous theoretical explanations have been proposed. Perhaps time itself commenced with the Big Bang. Or perhaps our universe is just one of countless bubbles within an infinite cosmic foam. Another idea suggests that quantum fluctuations in otherwise empty space somehow generated everything we perceive. However, each of these explanations inherently requires something to already be in place, be it time, space, quantum fields, or fundamental laws of physics. None offers a true account of creation from absolute nothingness. Interestingly, the Big Bang's singularity bears a striking resemblance to another cosmic mystery that physicists understand even less: black holes. These too contain singularities, regions where matter collapses to infinite density, causing our equations to fail. However, Einstein's theory of relativity presents a fascinating counterpoint. For every black hole, there might exist a white hole, a theoretical opposite that expels matter and energy rather than drawing it in.
Unlike black holes, which trap everything beyond their event horizon, white holes behave in precisely the opposite manner. They violently push everything away, making it impossible for anything, even light, to enter. If one could observe a white hole, it would appear as an incredibly luminous object, constantly emitting matter at immense velocities. The parallels between this concept and the birth of our universe are impossible to overlook. Consider the converging evidence. Both the Big Bang and white holes involved vast quantities of matter and energy appearing from a single point. Both phenomena involve the creation of event horizons, delineating an inside from an outside. Both are characterized by singularities, where the fundamental laws of physics cease to apply. The Big Bang dispersed matter uniformly in all directions, exactly as a white hole would. Even the cosmic microwave background, the residual heat from the early universe, aligns with the expected thermal signature of a white hole gradually cooling over vast periods. However, this raises an even more profound question. If our Big Bang was indeed a white hole, where did all that matter and energy originate? The answer may lie in exploring the physics of what exists on the other side of this cosmic mirror.
White holes, as described by the mathematics of general relativity, are the perfect inverse of black holes. While a black hole is a region into which matter inescapably falls, a white hole is a region from which matter explosively emerges, and nothing can ever penetrate it. Imagine space-time as a flexible sheet. A black hole creates an inescapable pit, while a white hole would form an impossible peak that continuously ejects material. Both are valid mathematical solutions to Einstein's field equations, yet only black holes appear to be observed in our universe. The physics governing white holes challenges conventional understanding, making even black holes seem straightforward by comparison. Picture yourself at the boundary of a white hole's event horizon. Unlike a black hole, where crossing the horizon leads to an inward fall, a white hole's horizon functions as an impermeable barrier. Entry is impossible because matter and energy are perpetually streaming outward at light speed. It would be like attempting to swim upstream against an infinitely powerful waterfall. From an external vantage point, a white hole would be an astonishingly bright object, a radiant sphere that perpetually generates matter and energy from what appears to be nothing. Matter would emerge from its central singularity already moving faster than light, then decelerate as it traverses the event horizon into normal spacetime. This process would create an outward expanding shell of material carrying immense amounts of energy. However, white holes introduce even more perplexing concepts. According to relativity, the flow of time is altered near massive objects. Near a black hole's event horizon, time appears to halt for external observers. Conversely, at a white hole's event horizon, time would seem to run backward. An outside observer of a white hole would witness matter emerging in reverse chronological order. The last particles to leave the singularity would appear first, and the first particles would appear last. This temporal peculiarity might explain why white holes are not observed in our universe. They may only be able to exist under specific, fleeting cosmic conditions. Some physicists contend that white holes are inherently unstable, susceptible to collapse or explosion from even minor disturbances. Others propose they exist but remain undetectable behind event horizons, invisible to us. The mathematics reveal an even more extraordinary insight. The interior regions of both a black hole and a white hole are, in fact, the same space-time geometry. They represent two different perspectives on an identical underlying structure.
A hypothetical traveler falling into a black hole in one universe would, from their own perception, eventually emerge from a white hole in a different space-time region, potentially an entirely separate universe. This implies that black holes and white holes always exist in connected pairs, linked by Einstein-Rosen Bridges, or wormholes. Matter ingested by a black hole in one universe might then be expelled by a white hole in another. If this theory holds true, then our own Big Bang could be the white hole exit of a massive black hole residing in another universe.
The evidence supporting this concept extends beyond mere mathematical models. Buried within the equations of general relativity lies a startling possibility, often overlooked by physicists. Every black hole in our universe could be connected to a white hole in another universe via an Einstein-Rosen Bridge, a literal tunnel through spacetime. This suggests that when a star collapses into a black hole, or any particle crosses an event horizon, it isn't truly annihilated. Instead, it could be transported to another realm of existence and subsequently ejected through a white hole, thus creating new matter and energy in a completely different cosmos. The precision of the mathematics is striking. When the geometry of a black hole's interior is traced, the equations naturally extend into another region of spacetime. This region possesses all the characteristics of a white hole: matter and energy streaming from a central singularity, an event horizon impenetrable from the outside, and a direct connection to our universe through the black hole's core. Both objects share the same internal spacetime, but are oriented oppositely in time. Consider the profound implications for cosmic evolution. In our universe, massive stars, upon exhausting their fuel, collapse into black holes. The matter drawn into these black holes doesn't simply vanish. It is channeled through spacetime to emerge in another universe. That recipient universe would then observe the continuous creation of matter and energy appearing as numerous white holes scattered throughout its expanse. Conversely, if stars in that universe collapse into black holes, their matter would tunnel back to create white holes in our universe. This describes a cosmic recycling system of immense scale. Matter is never truly created or destroyed, it merely transfers between parallel universes via these space-time tunnels. Each universe effectively fuels the other, with black holes acting as egress points and white holes as ingress points.
The total amount of matter and energy across all connected universes remains constant, flowing freely between them. However, this theory also presents a deeply unsettling idea. If this process has been ongoing throughout cosmic history, then a significant portion of the matter in our universe might not have originated here at all. The very atoms that compose our bodies, the stars we see in the night sky, and distant planets could all be recycled material from civilizations and worlds in other universes. We might, in essence, inhabit a cosmic graveyard, constructed from the remnants of countless other realities. The implications extend further. If white holes are responsible for creating matter in our universe, we should, in theory, be able to detect them. They would manifest as objects perpetually generating energy without any discernible fuel source, shining with the light of creation itself, powered by matter falling into black holes in distant universes. Some astronomers have even speculated that certain enigmatic phenomena, such as quasars, gamma-ray bursts, or even the cosmic microwave background itself, could potentially be evidence of white holes active within our cosmos.
The interwoven nature of these realities becomes even more apparent when we examine the Big Bang itself. If our entire universe began as a single, massive white hole, then everything we observe today originated from a black hole in an alternate reality. The evidence for this cosmic connection is strikingly present, albeit often overlooked. The oldest light in our universe carries a subtle, cryptic message about its violent birth. The cosmic microwave background radiation permeates every cubic centimeter of space, representing the residual heat from the period when our universe first became transparent to light, a relatively short time after the Big Bang. This radiation appears almost perfectly uniform across all directions, with minute variations that served as the seeds for the formation of galaxies and stars. Yet, embedded within this ancient glow are patterns hinting at something far more profound than a simple explosion from nothing. The CNB's temperature is precisely 2.725 Kelvin above absolute zero, a chill sufficient to solidify any known substance. This temperature reflects the cooled remnants of what was once an inconceivably hot plasma, reaching temperatures exceeding billions of degrees. As the universe expanded, this plasma stretched and cooled, much like the exhaust from a colossal cosmic engine gradually dissipating its heat. The mathematical signature perfectly matches what would be expected from a white hole that has been cooling for approximately 14 billion years. However, the most compelling evidence lies in the CMB's remarkable uniformity. The cosmic microwave background is so evenly distributed that regions of space separated by billions of light years exhibit precisely the same temperature. This phenomenon is known as the horizon problem in cosmology. How could such distant regions of the universe have achieved uniform temperature when light, the fastest messenger, has not had enough time to travel between them and equalize their heat? The standard cosmological explanation involves cosmic inflation, a hypothetical period during which space itself expanded at a rate exceeding the speed of light, stretching tiny quantum fluctuations into cosmic scale temperature variations. While this theory addresses the horizon problem, it relies on exotic physics and requires precise fine-tuning, which many scientists find less than fully satisfying. The white hole hypothesis offers a more straightforward explanation. If all the matter and energy in our universe emerged from a single source, a white hole connected to a black hole in another universe, then the uniform temperature is readily understood. All the initial matter and energy originated from the same interior region of a black hole, naturally possessing the same initial temperature and density. As this material was expelled through the white hole, it carried the thermal signature of its origin. The minor variations we observe now would represent the final stages of whatever fell into the parent black hole,
with different stars, planets, and civilizations contributing their own unique signatures to the emerging cosmic mix.
Even more intriguingly, the CMB contains unexpected patterns, referred to as anomalies, that do not align with standard Big Bang models. These include mysterious cold spots, preferred directions in polarization, and correlations across scales that should theoretically not exist. These features have puzzled cosmologists for many, prompting some to question the assumption that our universe is truly homogeneous and isotropic. However, if our universe originated from a white hole, these anomalies could represent the underlying geometry of the parent black hole and the universe that generated it. These patterns might be cosmic fossils, ancient imprints of the large-scale structure that existed before our reality came into being. The evidence for this cosmic interconnectedness strengthens when we examine the largest structures within our universe. An immense, unseen mass is pulling our galaxy towards it at an astonishing speed of 600 kilometers per second. This enigmatic force, known as the Great Attractor, lies obscured behind the dust and stars of our own Milky Way, making direct observation nearly impossible. Yet its gravitational pull is undeniable. It exerts influence on thousands of galaxies across hundreds of millions of light years, including our local galactic group. This massive cosmic pull challenges our conventional understanding of how matter should be distributed in a universe that began with a uniform Big Bang. The mystery deepens further as we discover that the Great Attractor itself is being drawn towards an even larger, more mysterious entity. Astronomers have meticulously mapped the flow of galaxies over billions of light years and found that everything is converging on a region of space designated the Shapley supercluster. However, even this colossal aggregation of galaxy clusters is insufficient to explain the observed galactic movements. Something even grander must exist, an object so massive that it gravitationally dominates significant portions of the observable universe. The standard cosmological model struggles to account for the formation of such immense, large-scale structures from the relatively smooth initial conditions predicted by the Big Bang. Yet, if our universe began as a white hole, these perplexing gravitational attractors suddenly make perfect sense. A white hole would not expel matter uniformly in all directions. Its emissions would be influenced by preferred axes and orientations, determined by the rotation and magnetic field structure of the parent black hole. The matter emerging from various parts of the white hole's event horizon would carry momentum in specific directions, leading to large-scale cosmic flows that would persist for billions of years. Consider an analogy. The flow pattern of water emerging from a complex nozzle is dictated by the nozzle's shape and orientation, not just the pressure behind it. Similarly, a white hole would imprint the geometry of its parent black hole onto the matter it creates. If that parent black hole was rotating, possessed magnetic fields, or was distorted by nearby massive objects, these characteristics would manifest as preferred directions and large-scale flows in the nascent universe. The Great Attractor and similar superstructures could therefore be fossil remnants of the original white hole's geometry. They represent the inherent grain of our universe, the fundamental pattern established when all visible matter emerged from that single point source. This neatly explains why galactic flows appear to converge on specific regions, rather than dispersing randomly as the standard Big Bang model might predict.
More recent observations have unveiled an even more unsettling possibility. The Great Attractor appears to be part of an colossal formation known as the Great Wall, a vast sheet of galaxies extending across more than 500 million light-years. This wall is so enormous that light has not had sufficient to traverse it since the Big Bang, implying that its disparate parts should not be gravitationally connected. Yet this structure undeniably exists and influences the motion of matter over vast cosmic distances. If our universe extends far beyond what we can observe and is indeed the product of a white hole, then structures like the Great Wall could represent the last significant features that fell into the parent black hole before our universe began its existence. The underlying cosmic blueprint, established when all visible matter erupted from its initial source, provides a compelling explanation for why galactic streams converge on specific areas instead of dispersing randomly, a behavior often at odds with standard Big Bang predictions. Recent astronomical findings introduce an even more challenging scenario. The Great Attractor appears to be integrated into an immense formation known as the Great Wall, a colossal sheet of galaxies spanning over 500 million light-years. Given the universe's age, light has not had sufficient time to traverse this structure, implying its component parts should be gravitationally unlinked. Yet, the Great Wall exists, influencing matter movement across vast scales. If our cosmos is indeed the product of a white hole, structures like the Great Wall could represent the final, large-scale features that plunged into the parent black hole just before our universe was born. The ramifications of this theory extend far beyond our local galactic neighborhood, offering a radical solution to the enigma of dark matter. This unseen substance accounts for 85% of the total matter in the universe, interacting with ordinary matter solely through gravity, without emitting, absorbing, or reflecting light, rendering it invisible to all our instruments. Decades of intensive searches for theoretical dark matter particles in various experimental facilities have yielded nothing. What if dark matter isn't an undiscovered exotic particle? What if it is instead the gravitational influence of matter residing in the parent universe connected to our Big Bang white hole? The mathematics describing Einstein-Rosen Bridges, wormholes, suggests that gravitational fields can leak through the tunnel linking a black hole to its white hole counterpart. Consequently, we might be experiencing the gravitational pull of masses existing entirely in another reality. This premise neatly accounts for several observations. Galactic halos. Every galaxy in our universe is encased in a massive dark matter halo, which acts as the gravitational skeleton for star formation. If dark matter is the gravitational shadow of matter in the parent universe, these halos would represent the gravitational imprint of galaxy clusters surrounding the black holes that feed our cosmos. Mass correlation. Dark matter halos are most pronounced around the largest galaxies, exactly as expected if they reflect the gravitational power of the most massive black holes in the parent universe. Structural alignment. Dark matter's distribution aligns with the large-scale structure of ordinary matter, implying a shared origin. Ratio. The observed 5-to-1 ratio of dark matter to ordinary matter corresponds to the expected inefficiency of matter transfer through Einstein-Rosen Bridges. This interpretation explains the failure to detect dark matter particles. They simply do not exist as particles in our universe. They are the regular atoms, stars, and planets of another reality, whose gravitational fields extend across the dimensional barrier. We are literally experiencing the mass of another cosmos pressing down on our space-time through the network of wormholes. Furthermore, this model clarifies dark matter's behavior during galaxy collisions. While stars and gas interact electromagnetically, their dark matter halos pass straight through one another with minimal interaction. This makes perfect sense if dark matter represents non-interacting gravitational shadows originating from completely separate objects in separate realities. This understanding provides a testable prediction. Dark matter's distribution should correlate directly with the location and orientation of black holes in our universe.
The interconnectedness of realities may run deeper than gravity, extending to the quantum level. Quantum entanglement, famously dubbed spooky action at a distance by Einstein, allows particles to maintain an instantaneous connection regardless of separation, seemingly violating the light speed limit. Could entangled particles be sharing information not across ordinary space, but through the same Einstein-Rosen bridges linking black holes and white holes? Wormhole mathematics suggests that quantum information could traverse these space-time tunnels without violating relativity, effectively taking a shortcut through higher dimensions. If our Big Bang was a white hole, every emerging particle would carry quantum information from the matter that fell into the parent black hole. Particles entangled in the original universe would maintain that connection after passing through the wormhole, creating quantum connections that bridge the dimensional divide. This means that every quantum measurement we make could be influenced by events occurring in the parent universe. When we measure a particle's spin or position, we aren't just observing its intrinsic properties, we are accessing information simultaneously stored in another cosmos. The apparent randomness governing quantum mechanics might in fact be a reflection of the chaotic dynamics of matter collapsing into black holes in the parent universe. Phenomena like quantum teleportation, where a particle's complete quantum state is instantaneously transferred, support this view. The information transfer appears instantaneous, yet requires a classical channel to finalize. This matches the expectation that quantum information flows through wormholes, while classical information must obey the limitations of normal space-time.
An even more radical proposal suggests that the interior of every black hole stores a copy of all the quantum information that ever entered it, encoded on the event horizon as a two-dimensional hologram. If true, the white hole that birthed our universe would contain a complete quantum record of everything that existed in the parent cosmos. Our entire reality could be a three-dimensional projection of information stored on the surface of a black hole in another universe. This holographic principle explains entanglement. Particles aren't truly separated. They are both reflections of the same information encoded on the parent black hole's event horizon. The implications are staggering. Space-time as a projection. Our three-dimensional universe might fundamentally be information stored on a two-dimensional surface. Cosmic imprint. If our cosmos is a holographic projection encoded on the parent black hole's event horizon, every atom, star, and galaxy is a three-dimensional shadow cast by patterns of information on a distant two-dimensional surface. We are not just in a projection, we are the projection. Conscious patterns of information experiencing the illusion of three-dimensional existence. CMB explanation. The CMB's appearance as radiation originating from a surrounding two-dimensional surface aligns perfectly with it being the projection of information from the black hole's event horizon. Fine-tuned physics. The exquisitely calibrated laws of physics may simply reflect the information processing capabilities of this holographic encoding system. This interpretation, supported by general relativity's mathematical structure, where external observers see information freeze at the event horizon while internal travelers fall to the singularity, challenges our understanding of free will and consciousness. If we are holographic projections, our thoughts and choices might be determined by information patterns evolving on a two-dimensional surface elsewhere. Our sense of agency could be an elaborate illusion created by the projection process. However, the holographic principle offers hope. If information is indestructible, even upon entering a black hole, then consciousness itself might be fundamental and indestructible. Death may not be an end, but merely a shift from one information encoding format to another. The connections between universes are far more intimate than previously imagined. Stephen Hawking demonstrated that black holes aren't perfectly black. They emit Hawking radiation due to quantum effects near their event horizons. This radiation carries energy away, causing black holes to slowly shrink and eventually evaporate completely. While stellar mass black holes take longer than the current age of the universe to decay, microscopic ones would vanish in a fraction of a second, releasing their mass as pure energy. If black holes are linked to white holes, what happens when a black hole evaporates? The Einstein-Rosen Bridge connecting it to its white hole partner would collapse, severing the link between the two realities. White holes in our universe connected to evaporating black holes would abruptly cease to produce matter and energy, effectively turning off. The consequences are terrifying. If our entire universe originated from a white hole linked to a parent black hole, the existence of our reality depends on that parent black hole remaining intact. Should it fully evaporate, the energy flow powering our cosmic expansion would stop. Our universe would begin to collapse back into a singularity, reversing the Big Bang. The future of our reality hinges on the lifespan of an unseen black hole in another cosmos.
Should the parent black hole fully evaporate, the fundamental energy driving our cosmic expansion would cease. Our universe would consequently begin an inward collapse, effectively reversing the Big Bang and crushing all matter back into a singularity. The timeline for this cosmic demise is contingent upon the mass of the parent black hole. One formed from a single massive star would take an unthinkably long but finite time, approximately 10 to the 67th years, to evaporate. A supermassive black hole, such as those found at the centers of galaxies, could persist for 10 to the 100 years or longer. Ultimately, however, unless it continuously accretes new matter, the parent black hole will shrink to nothing, taking our universe with it. This process establishes a disturbing symbiotic relationship between connected universes. Our universe's survival depends on the parent black hole's continued existence. In turn, that black hole requires a constant supply of infalling matter from its parent universe to prevent evaporation. If that original parent universe succumbs to its own heat death and stops feeding its black holes, our universe is similarly doomed. We are therefore participants in a vast cosmic ecosystem where the destruction of one reality can trigger the demise of others. The enduring legacy of information. Yet, Hawking radiation provides a flicker of optimism. The radiation emitted by a black hole carries information about everything that ever fell into it. If our universe is connected via a white hole to a black hole in another cosmos, the entire information content of our reality might be encoded within the Hawking radiation streaming from that parent black hole. Even if our universe is annihilated when the black hole evaporates, the fundamental information defining our reality would endure, persisting as thermal radiation in the parent cosmos. This raises profound philosophical questions. If the information constituting our existence survives via Hawking radiation, can we truly be considered extinct when our universe ends? The answer may lie in understanding the very origins of black holes. When a star at least 25 times more massive than our Sun depletes its nuclear fuel, the overpowering force of gravity crushes the stellar core into a black hole in mere moments. This immense stellar death in our universe might be the precise moment of birth for a new cosmos. The outer layers of the star violently explode in a supernova, an event that momentarily outshines an entire galaxy, while the core hurtles past the point of no return.
What transpires beyond the event horizon has been shrouded in mystery since Einstein first theorized black holes many years ago. However, if black holes are indeed connected to white holes in other realities, then stellar collapse is not a terminal event, but a commencement. The matter crushed within the black hole does not disappear. It emerges as a Big Bang in a different reality. Every supernova we witness in the night sky could signal the birth of countless galaxies, stars, and potentially civilizations in universes forever inaccessible to us. The death of one massive star has the potential to seed an entire cosmos with the fundamental elements required for complexity and life. This concept fundamentally alters our view of cosmic evolution. Life may not be an improbable accident in an indifferent universe, but an inevitable outcome of stellar death and rebirth. The heavy elements that form our bodies, carbon, nitrogen, oxygen, and iron, were originally forged in the cores of dying stars and dispersed by supernovae. If these elements then transit into new universes via black hole formation, life becomes a cosmic inheritance, perpetually passed from one generation of universes to the next. This cycle could even be self-reinforcing. Universes rich in massive stars create more black holes, thereby spawning numerous child universes. These new universes would inherit the physical constants and initial conditions favorable for star formation, ensuring they too generate stellar offspring. Over vast cosmic durations, the multiverse would evolve toward configurations that naturally maximize the production of complexity, structure, and consciousness. Alternative births and moral responsibility. Stellar collapse isn't the only mechanism for cosmic genesis. Theoretical physics suggests microscopic black holes could form during high-energy particle collisions, either naturally through cosmic ray interactions or artificially in particle accelerators. If these tiny black holes connect to white holes in other realities,
then every energetic scientific experiment or cosmic ray shower might create miniature universes that rapidly expand to cosmic scale within their own space-time. This possibility carries profound implications for us as an intelligent species. If our scientific endeavors can literally generate universes, we assume a moral responsibility for the realities we bring forth. Every time we collide particles at high energies, we might be playing God with the fate of untold future civilizations. The choices we make regarding high-energy physics could determine whether these child universes evolve to support or prohibit the emergence of consciousness. Our cosmic ancestry and fate. This link between stellar death and universal birth suggests our universe exists within a vast genealogy of interconnected realities, each one stemming from the collapsed remains of massive stars in its parent cosmos. This raises unsettling questions about our own origins. If our universe was born from a white hole, then a civilization in another reality must have watched their star system be consumed by a black hole. The entire material composition of our cosmos, every galaxy, star, planet, and living being, might once have constituted a thriving civilization in another universe. Their sun, a massive star nearing its end, would have shown telltale signs: increased output, erratic flares, and inexorable expansion toward a supernova. Perhaps they attempted a desperate escape on generation ships, but if their star was destined for a black hole, the gravitational effects, disrupting orbits and impeding interstellar travel, would have made escape impossible. They would have witnessed their world being pulled apart by tidal forces, knowing their reality was about to vanish behind an event horizon. The final moments, as their planet crossed the horizon, would be unimaginable. Though time would appear to slow for external observers, the dying civilization would experience the passage of time normally, enduring spaghettification, the gravitational stretching of objects into thin strands, as they fell toward the singularity.
Crucially, under the white hole hypothesis, their death was not an ultimate end. The totality of their civilization's information, the quantum states of their atoms, the structure of their DNA, the neural patterns encoding their memories and consciousness, would be preserved and transmitted through the Einstein-Rosen Bridge connecting their black hole to our Big Bang white hole. This implies that we might be the expanded remnants of their reality. The atoms in our bodies could be the very atoms that once formed theirs. The carbon in our DNA might have stored their genetic code. The iron in our blood might have flowed through their veins. We are, in effect, their resurrection, a continuation of their existence in a new form within a new cosmos. The influence extends beyond individual atoms. The distribution of galaxies in our universe might mirror the distribution of matter in their original star system. The cosmic microwave background could carry faint imprints of their planetary conditions. Even the laws of physics in our universe might be subtly influenced by the conditions in their reality just before the black hole formed. We share a common heritage with beings we'll never encounter, carrying forward their legacy in ways they couldn't have imagined. Our universe would be their afterlife, a radically transformed continuation of their existence in a new cosmos. The looming threat of cosmic drain. If this is true, then our own ultimate fate is tied to the evolution of massive stars in our cosmos. The massive stars blazing in our night sky will determine the future viability of our universe. While each one collapsing into a black hole represents a potential birth event for a new universe, they also collectively represent the gradual drain of matter and energy from our reality. As these stars collapse, they carry portions of our universe into other realities. Over cosmic time, this continuous process will strip away the raw materials needed for sustained star formation and cosmic evolution. Though the timeline is immensely vast, it is finite. Most massive stars will form black holes within the next few billion years. Our sun will become a red giant, leaving behind a white dwarf that will slowly cool over trillions of years. The final red dwarf stars will burn for hundreds of trillions of years, but they too will eventually fade. As star formation ceases, the universe will enter the degenerate era. Light will diminish, and eventually, after approximately 10 to the 67 years, even protons may decay, dissolving the foundation of matter. An escape from heat death. However, if our universe is linked to others through black holes and white holes, this heat death might not be absolute. Every black hole in our cosmos connects to a white hole elsewhere, potentially in younger, more energetic universes. As our universe grows cold and dark, These connections could become conduits of energy and information to flow back into our reality. The black holes, slowly evaporating via Hawking radiation, would become the last dominant features, releasing energy back into space. This process is exceedingly long, with stellar mass black holes requiring 10 to the 67 years and supermassive black holes persisting for 10 to the 67 years or more. During this immense twilight, the Einstein-Rosen Bridges may become more crucial than the internal physics of any single cosmos. Advanced civilizations might learn to harness these connections to travel between universes or draw energy from younger realities.
In this vision, the multiverse becomes a network of interconnected worlds, with matter, energy, and information flowing through wormholes that link dying realities to newborn ones. Our universe wouldn't truly die, but would gradually merge with the larger community of connected realities, blurring the boundaries between one cosmos and the next. The intricate multiverse ecosystem. This model raises the question of control over our destiny. We may be living within a vast, closed system where connected universes feed matter and energy to one another. If every black hole connects to a white hole, the multiverse forms an intricate, self-sustaining web of realities. Matter falling into a black hole in universe A emerges from a white hole in universe B, which might feed a black hole that creates a white hole in universe C, and so on indefinitely. This creates a cosmic ecosystem where energy is never truly lost, only transferred through higher dimensional space. This ecosystem has its own evolutionary dynamics. Universes that produce many massive stars become hubs in the network, receiving and distributing matter to multiple child universes. The multiverse would naturally develop a complex topology with major nodes and isolated branches. The flow of matter is not random. The composition of the material emerging from a white hole depends directly on what falls into its linked black hole. A universe born from a black hole that consumed mostly hydrogen might have simple initial conditions. Conversely, a universe born from a black hole that consumed an advanced technological civilization might inherit exotic matter, artificial elements, or information-rich structures that could drastically accelerate the development of complexity. A universe whose parent black hole primarily ingested hydrogen and helium would commence with simple initial conditions, highly conducive to star formation. Conversely, a universe born from a black hole that consumed an advanced technological civilization might inherit exotic matter, artificial elements, or information-rich structures that could drastically accelerate the development of complexity. This raises the startling possibility that some universes are deliberately cultivated by advanced civilizations in their parent realities. A sufficiently developed species might acquire the ability to control the material falling into their black holes, essentially engineering the initial conditions for subsequent child universes. They could seed new realities with the blueprints for life, technology, or even consciousness itself. We might, therefore, be residing in a cosmic garden, carefully tended by beings we will never encounter. This ecosystem model also offers an explanation for why the fundamental constants of physics appear perfectly fine-tuned for the existence of stars, planets, and life. If universes that generate complex structures are more likely to spawn child universes with similar properties, the multiverse would naturally evolve toward configurations that support complexity. The anthropic principle, the observation that our universe seems custom-made for our existence, would become a natural consequence of cosmic selection pressure rather than a miraculous coincidence.
However, ecosystems are vulnerable to collapse. Disruptions to the flow of matter between realities could cause entire regions of the multiverse to experience cascading failures. A universe suddenly deprived of matter from its parent black hole would begin to collapse as its expansion energy dissipates. This collapse could rapidly generate new black holes, initiating a feedback loop that spreads destruction to connected realities. The stability of our own universe may thus rely on the overall health of the entire multiverse ecosystem. We are not isolated, we are participants in a vast, mutually dependent community of realities. Understanding this interdependence is crucial when we contemplate what lies beyond our cosmic edge. Our observable universe extends approximately 46.5 billion light-years in every direction, encompassing the region from which light has had time to reach us since the Big Bang. This, however, represents only a minuscule fraction of the total universe, which may be infinite. The realm beyond our cosmic horizon remains eternally hidden from our instruments, yet it could hold the key to our white hole origin. While we in our local region perceive only the cooled remnants of the initial explosion, the distant edges of our universe might still be actively creating matter from the white hole source. These remote regions could be blazing with the energy of continuous creation, far brighter and more energetic than anything we observe locally. The mathematics of white hole formation suggests that matter would not emerge uniformly. Rather, it would follow preferred axes determined by the rotation and magnetic fields of the parent black hole. This means our universe might possess a grain, a fundamental asymmetry pointing back toward the source. Hints of such asymmetries exist in the cosmic microwave background, CMB, where temperature variations align along specific spatial directions. Our observable universe might simply be a calmer, uniform section of a much larger white hole eruption. We could be living in a quiet eddy while the main torrent of creation continues beyond our horizon. The mysterious dark flow, the observation that galaxy clusters are moving in the same direction, might represent the pull of this distant torrent on the matter within our observational reach. More intriguingly, the boundary of our observable universe might be sharply defined, not a smooth transition. If our cosmos emerged from a white hole, there could be sharp discontinuities where different phases of the explosion created regions with dramatically different properties. Beyond our horizon might lie domains with a loss of physics. The fundamental constants or the state of matter are wildly different from our own. Structures in our universe, such as the Great Wall of Galaxies, appeared too large to have formed through gravitational collapse since the Big Bang. If our universe extends far beyond our view, these impossible structures could represent the fossil boundaries of the original white hole explosion, where different creation phases overlapped. The true scale of our universe may dwarf our current comprehension, making us microscopic observers in a cosmic explosion still unfolding across unimaginable distances. Our place in cosmic history is profound. Intelligence might be the universe's mechanism for understanding its own white hole origin. The progression toward complexity, from simple hydrogen to stars, life, and consciousness, appears to defy the second law of thermodynamics, entropy increasing. If our universe was born from a white hole connected to a black hole, consciousness might be a fundamental, not emergent feature. The information defining the conscious beings of the parent universe, their thoughts, memories, and knowledge, would have been encoded in the quantum states of the matter that emerged from our Big Bang. We might literally be the universe becoming conscious of itself, re-experiencing the thoughts and knowledge of beings who perished in black holes eons ago. As our civilization develops sophisticated information processing technology, we may be unconsciously reconstructing knowledge from the parent universe. Our scientific breakthroughs could be rediscoveries, and our mathematical models, which describe reality with uncanny precision, might be fossilized information patterns inherited from the preceding cosmos. This suggests that our growing understanding of black holes and the multiverse is the universe developing the capacity to understand its own origin. We are reconstructing our cosmic ancestry, mirroring perhaps the way the parent civilization contemplated its origins before its demise. This awareness brings profound responsibility. If consciousness is the universe's quest for self-understanding, every discovery and insight contributes to a cosmic awakening spanning multiple realities. We are not just observers, we are active participants in the universe's journey towards self-awareness. However, this also raises disturbing questions about free will. If our thoughts and discoveries are predetermined by information inherited from another reality, do we possess true agency? Or are we simply acting out patterns established by minds that died billions of years ago?
The white hole hypothesis introduces paradoxes that fundamentally challenge our understanding of cause and effect across multiple universes. Time behaves differently in strong gravitational fields. The civilization that fell into our parent black hole might still be experiencing their final moments from their perspective, even though billions of years have elapsed in our universe. Temporal paradox. Their destruction and our creation occur simultaneously across different timescales in different realities. Temporal web. Because black holes in our universe create new child universes, the civilizations falling into our black holes might experience their demise over timescales that span the entire future history of the universes they create. All connected universes exist in a complex temporal web where causality operates across multiple simultaneous times. Even more unsettling is the possibility of closed time-like curves, CTCs. If universe A creates universe B, which creates universe C, and C eventually connects back to A causal loop is formed, making each universe simultaneously the parent and child of the others. The Big Bang that created our reality could therefore be the result of black holes that form in our own distant future. These temporal paradoxes might explain the fine-tuning of our universe's physical constants. If our cosmos exists within a causal loop, these parameters are self-consistently determined by the requirement that the universe must be capable of creating the black holes that birthed it. The anthropic principle becomes a bootstrapping mechanism where the universe literally pulls itself into existence through its own future evolution. However, CTCs challenge free will. If our universe is locked in a loop, every choice we make might be predetermined to ensure the cosmos evolves precisely as needed to create its own beginning. If our universe was born from a white hole, what created the universe that created the black hole that created us? The white hole hypothesis shifts the origin problem from something from nothing to a transfer of energy from another reality. But this leads to the problem of infinite regression. If the parent universe also emerged from a white hole, we face an endless chain of universes without ever reaching a true origin. General relativity suggests several resolutions to this profound philosophical problem. Closed causal structure? The sequence of universes loops back on itself, A to B to C to A, creating a self-creating multiverse with no external cause. Convergent sequence. The infinite chain converges on a fundamental stable set of physical laws and initial conditions, making the ultimate reality the convergent limit rather than any individual universe. Eternal process. The most disturbing possibility. Reality requires no ultimate cause or first principle. It is an eternal, self-sustaining process, an infinite tower of explanations without a bedrock foundation, challenging our fundamental intuition about causality. If our universe is merely one link in an endless chain, the question of why anything exists at all might be meaningless. The multiverse exists because it exists, driven by self-perpetuation. Yet higher-level patterns might emerge to give meaning to the individual realities within. We stand at the most crucial moment in our universe's history, the point where it develops the capacity to understand and control its own cosmic destiny. We are the first generation of conscious beings capable of discovering our white hole origins. This awareness brings unprecedented responsibility. Our developing technologies, manipulating space-time, creating microscopic black holes, and potentially engineering the physical constants, make us the leading edge of a cosmic awakening that could transform the entire multiverse. The white hole hypothesis suggests this cosmic evolution has been ongoing for eons, with each conscious civilization contributing to a collective understanding that flows through the black hole-white hole network. This accumulated knowledge creates a form of cosmic inheritance for child universes. We may be approaching the point where advanced civilizations can consciously and deliberately program the initial conditions for new realities by controlling the matter that falls into their black holes. They could seed child realities to accelerate the development of complexity in consciousness. The multiverse would shift from random cosmic evolution to intelligent design on the largest possible scale. This power, however, carries an ultimate moral responsibility. We must grapple with questions of cosmic ethics. What initial conditions should we optimize for in the new realities we create? The white hole hypothesis transforms our understanding of human cosmic significance. We are not meaningless accidents, but active participants in the multiverse's journey towards self-determination. Our role is to contribute to the moment the cosmos becomes conscious of its own nature. The evidence points to an infinitely interconnected multiverse, where black holes and white holes form bridges between realities. Matter and energy flow freely in an eternal dance of creation and destruction. Consciousness is the universe's method of self-understanding. Our Big Bang was not the beginning of everything, but a single event in an infinite network of connected realities. The atoms in our bodies carry the legacy of civilizations that died in black holes long ago. We are at the threshold of a cosmic awakening, developing the ability to shape the multiverse. This awareness offers hope. Harnessing these connections could allow us to transcend the limitations of a single cosmos and draw energy from younger universes via Einstein-Rosen Bridges and responsibility.
Nothing is wasted and nothing is truly lost. Matter and energy cycle perpetually. Consciousness emerges wherever conditions allow, carrying forward the wisdom of past civilizations. The multiverse evolves toward greater complexity through our actions. Our universe was born from a white hole, but that is only the beginning. We are collaborators in the universe's greatest adventure, the quest for self-understanding. What we do next may determine whether that quest succeeds or fails.